Hey, welcome back to your favorite calculus class. We're going to take a look at the chain rule. Here's our notation for the chain rule. We've introduced this before. So if we have a composite function, composite function f of g of x, then the derivative of f of g of x is f prime of g, and then times g prime of x. Right? So f is the derivative of g is derivative of f at g times the derivative of g at x, right? All right, so like without the chain rule, you need no chain rule here, if you will. Y prime is just 2x plus 0, right? Whereas if you have x squared plus 1 to the 1/2, right? Square root of x squared plus 1. Now when you take that derivative, you got to run the power rule. So 1/2 goes in front, x squared plus 1 to the negative 1/2, but this is a composite function. We don't just have x in there, we have x squared plus 1, so that derivative is 2x. And then you clean that up, right? Y equals the sine of x. No need for the chain rule. And by the way, you're always actually using the chain rule because every function can be written as a composite function. The derivative of the sine is the cosine, and then the derivative of the inside derivative of x is just 1. It's just that it doesn't make any difference when you just have x there, right? Now, it does make a difference when you have something besides x in there, like sine of 6x. You take that derivative, cosine 6x, and then times 6. So you want to write that as 6 cosine 6x. Let's keep going here. We got y equals 3x plus 2. Its derivative is 3. Of course, derivative of 2 is 0. That's no chain rule. But if you've got 3x plus 2 to the 5th, now when we take that derivative, we run power rule, 5, and this stuff to the 4th. And remember, we don't have x in there. This is a composite function, so we got to take the derivative of the inside, which is 3. Derivative of 3x is 3, derivative of 2 is just 0. So this just ends up being 15 times 3x plus 2 to the 4th. Alright, let's do this last one. This derivative here, 1 plus derivative of the tangent secant squared. Whereas over here, the derivative is 1 plus, now this is tangent of x squared, so it's secant squared of this x squared, and then derivative of x squared, 2x. So this is 1 plus 2x secant squared of x squared. Okay, that's some examples with the chain rule. All right, so the question is, can you decompose the functions? Can you think of what f of g of x and what g of x is? Okay, and I'm going to use the notation f of u and g of x. So for example, what are the two functions that make up y equaling 1 over x plus 1? What's the root function, I'll call it? F of u is 1 over u, and g of x is that x plus 1. That x plus 1 is going to go in there for u because here u is g of x. In other words, when we combine those, f of u, right, we're putting g of x in for u, then we're plugging g of x into u. Into f, I'm sorry, g of x into f. What's f? 1 over u, but what's going in there? G of x is, which is x plus 1. See how that's the same function? So the question is, can you decompose the functions? Like here's the next one, y equals the sine of 2x. You say, well, sure. F of u is just the sine of u, and that means g of x is that inside part, 2x. The third one, if y equals the square root of 3x squared minus x plus 1, f of u is just the square root of u, and then g of x is the stuff that goes in there for u. 3x squared minus x plus 1. Last one, what about y equals tangent squared of x, or tangent of x quantity squared? Well, f of u is the tangent of u. G of x then, I'm sorry, good grief. F of u is u squared. G of x, what's going in for u? Tangent of x is going in for u. So it's tangent of x quantity squared when tangent of x replaces the u there. Okay. Alright, if you remember, the derivative of a to the x is ln of a times a to the x. But now here we've got a composite function. So when we run this derivative, we got ln of e to the negative 5x, but that's not just an x up there. So we got to run the derivative of negative 5x, which is negative 5. Now the ln of e is just 1. So we got 1 times negative 5 times negative e to the negative 5x. So we got negative 5 e to the negative 5x. There's our derivative. Let's do it here. We've got another composite function. So when we take the derivative, this is kind of like u cubed, right? If we were taking the derivative, we'd have 3u squared. So when we take the derivative, we have 3, and then we've got 3x minus 2x squared, and then we take the derivative of the inside, which is 3, derivative of the inside, minus 4x. So it's just 3 minus 4x, 3x minus 2x squared. There's our f prime of x. Alright, how about x squared times the square root of 1 minus x squared? We run this derivative, so we got derivative of the first times the second plus the first derivative of the second. So this is, remember, this is square root of 1 minus x squared, so it's 1 minus x squared to the 1/2. So we've got 1/2 1 minus x squared to the negative 1/2 times negative 2x, derivative of the inside there. So we've got 2x squared to 1 minus x squared, and then we've got those 2's cancel right there. So I got negative x cubed over square root of 1 minus x squared. Now this is over 1 right now, so I'm going to give it a common denominator. So square root of 1 minus x squared, square root of 1 minus x squared. So I've got 2x, and that times that is just a regular old 1 minus x squared, 1 power, minus x cubed over square root of 1 minus x squared. I'm going to distribute that, so I have 2x minus 2x cubed minus x cubed all over square root of 1 minus x squared. So we got 2x minus 3x cubed over square root of 1 minus x squared. Take an x out. And there we are. Alright. Alright, next one here we've got derivative of the top times the bottom. Here's the bottom, third root, right, to the 1/3. Minus the top, numerator, times derivative of the bottom. So we got 1/3 x squared plus 4 to the 1/3 minus 1. So that's a negative 2/3 times derivative of that, which is 2x. And this is all over x squared plus 4 to the 1/3 squared. So we've got the third root of x squared plus 4, so x squared plus 4 to the 1/3. Then we've got minus 2x squared over 3 x squared plus 4 to the 2/3. This is all over x squared plus 4 to the 2/3. Now this is over 1. I gotta get the common denominator so I can combine these here. So I'm going to give this a 3 x squared plus 4 to the 2/3. 3x squared plus 4 to the 2/3. So this will become x squared plus 4 to the 2/3 times x squared plus 4 to the 1/3, x squared plus 4 to the 3/3, or x squared plus 4 to the 1. This is all over the common denominator. And then this is all over that x squared plus 4 to the 2/3, which is over 1, meaning keep change flip, so that'll become right there. Go right there. So x squared plus 4 to the 2/3 times x squared plus 4 to the 2/3 leaves us with our denominator being x squared plus 4 to the 4/3. And then I'm going to distribute this, so 3x squared minus 2x squared, I just got an x squared plus 12 in my numerator, and this is all equal to f prime of x. Alright, a couple more here. Take this derivative, I've got 2, and I've got this junk, right, so I'm running power rule. Now it's to the 1 power, but then I got to take the derivative of the inside, which means I got to run my quotient rule. Derivative of the top times the bottom minus the top, derivative of the bottom all over bottom squared. So what we've got is, and I'm going to go ahead and distribute this here as well as that negative through. Okay. Combine those. There's our y prime. Alright, a couple more here. We got sine 2x, so y prime would be cosine 2x, but then it's times. We got the chain rule there. Derivative of 2x is 2, so 2 cosine 2x. Next one, dy dx, derivative of cosine, negative sine of x minus 1. Derivative of x minus 1 is just a 1, so that makes no difference. 1 minus 0, of course. Derivative of the tangent, so y prime derivative of tangent is secant squared of 3x, but then derivative of 3x, 3. So this is 3 secant squared 3x, that's our y prime. Well, thank you so much for listening.